In this video, we're going to be talking about matrix multiplication. So in this last chapter of the course, we've switched away from calculus and we're talking about matrices. The overview of what we're doing in this chapter is we're working towards solving systems of equations. So in this section, we're going to talk about how to multiply two matrices together, and that's going to help us move forward towards solving systems of equations. So let's start with a formula. We're going to look at an operation called the dot product that allows us to multiply a row of a matrix with a column of a matrix. So we're going to write down the row, we're going to write this dot operation, and we're going to write down our column. And the way the operation works is you're going to multiply your first two numbers together, so 1 times 1. You're going to multiply the second pair of numbers, so the 3 times the 5, and you're just going to add the result. So you go 1 times 1 plus 3 times 5, and that gives us 16. So what the dot product does is it takes a row of a matrix, multiplies it with a column of a matrix, and spits out a number. So you could do this even if your rows and columns were bigger. You could have a row of 3 numbers and do the dot product with a column of 3 numbers. So the pattern is the same. You multiply the first pair of numbers together, and then you add on the product of the second pair of numbers, so the 4 times the 6, and then you add on the third product, the 1 times the 2. So if you put all that into your calculator, you'd have the number 25 for your dot product. So now that we've seen that, let's get an overview of how we can multiply two matrices together, and then we'll do some examples. So let's look at these two matrices here. We've got matrix A and matrix B. The idea is anytime you want to multiply two matrices together, think about circling the rows of your first matrix. So circle all the rows in here. And then think about circling any columns in your second matrix. And the reason we're doing this is because we're setting ourselves up to do a dot product, and we know that the dot product takes a row, multiplies it by a column. Okay, and then let's think about how to build the product A times B. So what you're going to see inside this product is just a bunch of dot products. So when we write things like R1, R2, R3, we're talking about the rows of A. And when we write things like C1 or C2, we're talking about the columns of B. As for specifically which row and column to multiply together, just look at any position in this matrix, let's say this position here, and just figure out which row and column it's in. So this is in position row 2 and column 1. Therefore, we're going to be taking row 2 of our matrix A, and we're going to be doing the dot product with column 1 of B. So you could just say you're doing the dot product of the appropriate row with the appropriate column corresponding to what position you're in your matrix. So if you were in this position here, we'd say, well, that's row 3 and column 2. So we'd be taking row 3 of A and doing the dot product with column 2 of B. So now that we've seen that overview, let's jump into a fresh page and we'll actually try this computation. So here we have matrix A and matrix B, and the problem is to find the product A times B. So we're going to circle the rows of our first matrix, and we're going to circle the columns of our second matrix. And the idea is that AB is going to contain a whole bunch of dot products. But as for which dot product to do in which position, just think about which position we're in. So if we're in the row 1, column 1 position, we're going to take row 1 of A dotted with column 1 of B. Okay, so maybe let's just do a little bit of work on the side and show what that would look like. So I'm going to highlight the first row of A and the first column of B, and we're just going to do that dot product. So we'd multiply the 4 times the 1 plus the 6 times the 1 plus the 1 times the 2. So that would give us 12. And then if we wanted to move over to this position, well, we'd say that's row 1, column 2 position. So we're going to take row 1 of A and dot with column 2 of B. So let's fill in the details here. We're going to go 4 times 0 plus 6 times 1 plus 1 times 3. So that's going to give us 9. So sort of the fast way to think about this is if I want to fill in this next row here, that's row 2. So what I would think about doing is taking row 2 of the first matrix, and then we're going to imagine doing the dot product with the various columns of B. So as we work our way across the various columns of B, we'll be filling in this row. Okay, let's say we wanted this position here. We would say that's row 2, column 2. So we're going to take row 2 of A with column 2 of B. Let's fill in the details there. So that's going to be 0 times 0 plus 2 times 1 plus 3 times 3. So that's going to give us 11. If we wanted this position here, for example, we'd say that's row 3 and column 1. And we'd go 1 times 1 plus 1 times 1 plus 1 times 2. So that would give us 4. So if we were to fill in the other details here, in row 2, column 1 position, you'd be doing this dot product here, row 2 with column 1. So that's going to give us 8. And if we wanted this entry in the bottom right-hand corner, well, we'd say that's row 3, column 2 position. So we would highlight row 3, column 2, do that product, and that's going to give us 4. So there we have our very first example of multiplying two matrices together. So we'll do a few more computations like that in a minute, but while we're on this example, I want to talk about the size of AB, because it's nice to be able to predict what the size of your matrix is going to be in advance. So size, number of rows times number of columns. So our size of AB came out to 3 by 2. Let's see if there was a way to predict that based on the two matrices that we started with. So let's look up at matrix A here and matrix B and think about their sizes. So A was 3 by 3 and B had 3 rows and 2 columns. So that was 3 by 2. In order to multiply two matrices together, the inside numbers must be equal. So if you ever have a situation where these two inside numbers are not equal, we'll see in a later example that you just aren't able to multiply the two matrices together. The sizes are incompatible. So those inside numbers must be equal. And then the outside numbers predict the size of the product. So the size of AB just comes from looking at the first and the last number here, 3 by 2. And sure enough, AB is 3 by 2. So that's how we can predict the size of AB in advance. So then sticking with these same two matrices, you might ask, I wonder what would happen if I tried to multiply them in the other order. So let's see what would happen. You take your matrix B, which is 3 by 2. You try to multiply it with a matrix that is 3 by 3. So let's write down what the sizes would look like. So you'd have 3 by 2 for B, and you'd have 3 by 3 for A. Okay, and notice that these inside numbers are not equal. And that tells us that we actually can't multiply B times A in this order. So let's try to understand why. Sometimes when I'm thinking about matrices, I'll just draw a little dot or star or something to represent the position of the numbers here. But what we're focusing on is the fact that B has just 2 columns and A has 3 rows. So imagine what would happen if you tried to do a dot product. If you tried to multiply this row with this column using the dot product, you just wouldn't be able to do it. You've got 2 numbers here that somehow need to be multiplied with 3 numbers here, and our dot product can't do that. So we say BA is undefined. So let's make a connection here and just understand that when these 2 inside numbers here are not equal, that's just an algebra way of saying there's incompatible sizes in how many columns you have here and how many rows you have here. So it's just representing the situation in this picture at the top of the screen that's telling us that we can't compute that matrix product. So now we know that we need the inside numbers to be equal in order to multiply matrices together, and we know that the outside numbers are going to predict the size of the product. So AB came out to a 3 by 2 matrix, whereas BA doesn't exist at all. It's not defined. So really important fact when it comes to matrices is that AB is typically not going to be the same thing as BA. So we'll say AB is not equal to BA in general. You may be able to find isolated examples where AB equals BA, but if you just grab any 2 random matrices, most likely the order of multiplication is going to matter. So here's our next example. We have 2 matrices, C and D, and we're going to try to multiply CD and DC if possible. Okay, so let's start with CD. So what you might want to do is just think about sizes before you do the actual multiplication. So C is a 2 by 4 matrix, and let's think about what would happen if we multiply that by a 2 by 2 matrix. Well, these inside numbers are not equal, and that tells us that CD is undefined. In other words, it doesn't exist. So if you want a visualization of what we're saying here with these numbers, another way to think about it is just take your matrix C here, and then beside that write down your matrix D, and imagine what it would look like if you tried to do a dot product. So you'd have 4 numbers here that somehow need to get multiplied with 2 numbers here, and because of that mismatch, you can't do that dot product. So that's all we're saying. When these inside numbers are not equal, you can't perform the dot product, and your product is undefined. So let's try DC. So let's say DC equals, okay, well, D is going to be a 2 by 2 matrix. C is a 2 by 4 matrix. So if we just think about the sizes, 2 by 2 times 2 by 4, yep, the inside numbers are equal, and the outside numbers are going to predict the size. So we know at the end of the day, we're going to have a 2 by 4 matrix for our answer. So it's kind of handy to be able to predict in advance what size your product is going to be. So I'm going to write down all the numbers here. So D was 1, 0, 3, negative 1, and C was 1, 2, 3, 6, 1, 1, 0, 1. All right, so let's circle our first row. And we're going to take that first row and we're going to do dot products with the various columns. And as we do that, we're just going to be working our way across the first row of our product. So doing our dot products here, you'd have 1 times 1 plus 0 times 1. It's going to give us 1. Then for the second one, 1 times 2 plus 0 times 1, going to give us 2. Next dot product is going to be 3, and the next one will be 6. So we're just doing the dot products with the various columns here. Okay, and then let's try the same thing for the second row. So now we're working with the second row of our first matrix and then doing dot products with the various columns. So our first dot product would look like 3 times 1 plus negative 1 times 1. So that's going to be 2. Next dot product is going to be 5. And then we get 9 and 17. So A is a 2 by 2 matrix, and we're going to find A squared. Well, what A squared means is just multiply A times A. So I'm going to write out a copy of A, and beside that another copy of A. So we'll just fill in our matrix A here. And then in the usual way, we're going to be circling the rows of our first matrix with columns of our second matrix. So usually what I'll do is I'll just work with the first row of the first matrix and then do the dot products with the various columns. And that's just going to generate the first row of this product for us. Okay, so let's try our dot products. 1 times 1 plus 9 times negative 4. That's going to be negative 35. And our second dot product, 1 times 9 plus 9 times 3, is going to give us 36. For the bottom row, I'm going to be working with the bottom row of our first matrix and doing some dot products with the various columns there. So negative 4 times 1 plus 3 times negative 4, that's going to give us minus 16. And then finally for the bottom right corner, minus 4 times 9 plus 3 times 3 is going to give us a negative 27. And there we have our matrix product, A times A, or you could call that A squared. So matrix multiplication feels pretty weird, right? I mean, the first time I saw it, I thought it was pretty weird. I still, on some level, think that it's kind of weird, but there's a very good reason why we multiply like this. So let's talk about that. So why do we multiply this way? Well, to illustrate this, let's take a matrix A that just has some numbers in it. Let's take a matrix X, which just consists of a single column that has some variables in it. And let's take another matrix B that, again, just consists of a single column but has some numbers in it. So the idea is that we want to understand this equation, AX equals B. So let's plug in our A, X, and B into this equation and just see what happens. So A, as we said, is this square matrix that has some numbers. X is just a column that has some variables in it, and B, a column that has some numbers in it. Okay, so let's try to make sense of this equation that we've got highlighted here. So in order to make sense of that, we're just going to actually do a matrix multiplication. So we're going to circle the rows of the first matrix, and we circle any columns of the second matrix. So there's just one single column there. And we're going to do our dot products. So it would look like 1 times x minus 4 times y. So there we go. And then for the bottom row, it would look like 2 times x plus 3 times y. So there we go. And our equation is saying this is equal to 7, 6. Okay, and then we know what it means for two matrices to be equal. Basically, you're getting one piece of information from each position in the matrix. So one piece of information is that x minus 4y equals 7. And the other piece of information is that 2x plus 3y equals 6. And if we just describe this object that we've just created here, we would say, well, this object that we've just created is a system of equations. So back in the day when people were getting really interested in solving systems of equations, and I'm talking 150 to 200 years ago, let's say, there was interest in, how can we find a tool to help us solve systems of equations quickly? So the idea was, well, maybe we can take a system of equations and somehow represent it using matrices. So we wanted to take this system of equations and write it some way like ax equal b, just to come up with a quicker way of writing systems of equations. So then the question became, well, if we start with this system of equations here, start with something like this, what operation would we need to be able to write this back in this concise form, ax equal b? So this process here was reverse engineered. We basically said we want to go from the system of equations and move back up into something that looks like ax equal b. So if you just trace back through the algebra here, this tells us how matrix multiplication should be defined. So if the question is, why do we multiply like this? Then the answer is so that we can solve systems of equations. So the idea is that now there's this fast way of moving between systems of equations and this type of equation here, which we're going to call a matrix equation. So we can basically encode a system of equations by just writing down the coefficient matrix, then writing down a matrix that contains the variables and saying that's equal to a matrix that contains the constants. So if you want to write that symbolically, you would just write that ax equal b if you sort of wanted to talk about it without saying too many details. So to see if we've absorbed this idea around a matrix equation, let's do a little example. So someone has given us a system of equations, and the question is, write it as a matrix equation. So the way this works is you want to have a matrix that represents your coefficients. Then you want to have a matrix that is a single column that contains your variables. So I'll say variables, and then in brackets I'll just put columns so that we know we're writing those vertically. And then you say that's equal to, and then you have a matrix that contains your constants, so meaning the numbers from the right side of the system. And again, that's written in the form of a column. So let's pull the coefficients out of the system, just writing them down in the same position as they were in the system. We'd have 2, -9, 7, and 3 for our coefficients. Then write down your variables in the same order as they were given in the system. And then we're saying that's equal to the matrix that contains the constants from the right side of the system, 12 and -16. And that's written as a column as well. So you might wonder, okay, why is it so important that we write these variables here as a column instead of as a row, for example? Well, remember that size matters when you're multiplying matrices. So in order to do this multiplication, when you're taking a 2 by 2 matrix, you need to multiply it with a column, a 2 by 1 matrix. If this xy were written as a row, then you would have an incompatible multiplication. So that's why we have to be careful about that. All right, so what was given to us in the problem was a system of equations, and what we've managed to do is just write it in this more concise form using matrices. So we call this a matrix equation when we write it in this form. And if we wanted to talk about that matrix equation just briefly, without talking about all the details, then symbolically we would call that ax equal b. So a just represents your coefficients, X represents your variables and B represents your constants. So in order to move towards solving systems of equations, we need a couple more definitions in this section. So the next definition we're going to look at is the idea of the identity matrix. So let's put a box around this, call this a definition. So an identity matrix or identity matrices, there's actually a family of these identity matrices depending on the size of the matrix. So let's look at the 2 by 2 situation first. When we talk about an identity matrix, the symbol we're going to use is I. And what the matrix looks like, it's a square matrix that has ones along the main diagonal from the top left to the bottom right, and it has zeros everywhere else. So your 2 by 2 identity matrix looks like this. If you were doing a problem involving 3 by 3 matrices, you would still call your identity matrix I, but it would now be a 3 by 3 matrix. Pattern is the same, that it's got ones along the main diagonal from the top left to the bottom right and zeros everywhere else. We don't too often work with 4 by 4 matrices, but if we did, we would still call the identity matrix I. It would still have ones along that main diagonal and zeros everywhere else. So this matrix I is actually pretty important when we're solving systems of equations. So let's look at the main fact. So if you take the identity matrix I and you multiply it with A, you are going to get the matrix A. And that's for any matrix A that you're starting with. So let's just try a quick example to confirm that that's true. So let's confirm that I times A equals A for this matrix A here. Okay, well, if we want to confirm that this equation is true, we're just going to start with IA, and we're going to see if we can turn it into A. So let's think about this. The identity matrix has ones along the main diagonal from the top left to the bottom right. It's got zeros everywhere else. And we're going to multiply that with our matrix A, which is 9, 8, 2, 3. Incidentally, we know that we need the 2 by 2 version of the identity matrix because if we took a 3 by 3, then the sizes would not be compatible for multiplication. Okay, so just from the context, we can figure out that we need a 2 by 2 matrix there. So let's actually do our matrix multiplication, and we'll confirm that it comes out to A. So multiplying in the usual way, we're just going to take the first row of our first matrix, and we're going to do dot products with the various columns. So we're going to get 9 and 8. And then if we work with the second row of our first matrix and do some dot products, that's going to generate the second row of our product. So 2, 3, and yep, sure enough, that comes out to the original matrix A that we started with. So we'll store this fact away for a moment. We'll talk about it a bit later in the video, that I times A is going to equal A. So one more definition that we need in order to work towards solving systems of equations. So let's say we're given a square matrix A. So when we say square, it just means it got the same number of rows as columns. So just imagine 2 by 2 or 3 by 3 matrix. We're going to define this matrix called A to the negative 1. Okay, so A to the negative 1 has the property that when you take A and you multiply it by A to the negative 1, you get the identity matrix. And this is actually true if you did the multiplication in the other order as well. So A to the negative 1 times A equals I. Now, the proper name for this matrix A to the negative 1 is called the inverse of A, or we sometimes say A inverse. So in order to talk about the inverse matrix, the matrix that you're starting with must be square. It doesn't make sense to talk about the inverse of a non-square matrix. So before we get too far into the details here, let me just show you a parallel with real numbers. So imagine you had, let's say, the real number 3. If you multiply 3 by 3 to the negative 1, then what you get is the number 1. So multiplying by 3 to the negative 1 is somehow like undoing multiplication with 3 and giving us back the real number 1. And in a sense, that's what's happening with these matrices. Matrices are a little bit more complicated because they're not a single number. They have multiple numbers in them. But the underlying idea is still the same, that somehow you're taking this inverse matrix, you're multiplying it with the matrix A, and what you're getting back is the identity matrix. So the identity matrix in the matrix world is sort of like the number one, and the inverse matrix is sort of like the matrix version of taking a reciprocal in a sense, just to kind of give you a bit of intuition. So let's take a quick look at this note here. Some square matrices don't have an inverse. So unfortunately, not every square matrix is guaranteed to have an inverse. And we'll talk more about that as we go through chapter 16. So we're going to do a couple short examples here just to practice this idea of the inverse of a matrix. So in this example, we're given a 2 by 2 matrix A, and we want to just confirm that this matrix here is the inverse of A. Okay, so let's think about how we do that. Let's think about the key property that a matrix inverse has. The property is that A inverse times A should equal the identity matrix. So our job is just to check that this is true. Now, incidentally, you could also check that this is true the other way around. So anytime you have a matrix inverse, the order of multiplication doesn't matter. So you can check A times A to the negative 1 equals I if you prefer that, and you only need to check one. So you don't need to check both equations. Once you have one, the algebra just guarantees that the other one will also be true. So my default one, I usually like to check this version. Okay, so when you're trying to confirm that an equation is true, just start with the left side, and we'll just work our way through some algebra, and we'll confirm that this comes out to I. So we're given in the question the matrix that we want to confirm to be A inverse. So it's 9, 4, 2, 1. And we're given the matrix A. So 1, negative 4, negative 2, 9. So the idea is just to do our matrix multiplication in the usual way. What we're trying to confirm is that this comes out to the identity matrix. So that's the matrix with ones along the diagonal and zeros everywhere else. So let's confirm that. Take the first row of our first matrix, and we're going to do dot products with our various columns here. So we do get 1 and then 0. That looks good. And then for the bottom row, let's take this guy here and do dot products with the various columns. Yep, we do get 0 and then 1. So I'm going to put a check mark here and say, yes, this does come out to the identity matrix. You can just write I symbolically if you like. So all we're really doing in this example is just practicing the definition of the inverse matrix. Key formula that you want to keep in mind is just that when you take your inverse matrix and you multiply it by your original matrix, you get the identity. So that's all we're confirming there. In our previous discussion, we said not every square matrix has an inverse. So let's see an example of a square matrix that does not have an inverse. So something like A equal 1, 0, 0, 0 has no inverse, and let's just try to understand why. So let's think about whether there could be a matrix that we could put here to multiply with our matrix A to give us the identity matrix. That's the idea. If A had an inverse, then we would be able to find this matrix A inverse so that when it multiplies with A, we get I. Okay, so we're basically asking, is there a matrix out there that could work? Where the problem lies is in this bottom right-hand corner. So let's think about how we would build this 1 here that we've got highlighted. Well, that would come from taking the bottom row of this mystery matrix and doing a dot product with this column here. So doing the dot product there is what would generate this 1. So we just have to ask what numbers could we put in here so that when we do our dot product, we get 1. And there are no numbers that would work. So having this entire column of zeros is what's causing the problem. There are no numbers that we could put here to create that 1. So I'm just going to say this is impossible, and that's why this particular matrix A has no inverse. So what we'll see as we move through chapter 16 is that if a matrix has an inverse, that gives us a quick way of solving systems of equations. But unfortunately, some matrices won't have inverses, and in that case, we'll see a second method for solving a system of equations. So we've seen a bunch of big ideas in this video already. We've seen how to multiply matrices together. We've seen the idea of the identity matrix, and we've seen the idea of the inverse matrix. And to me, it feels like, we've done a fair number of definitions in this video. So I want to give you a little preview of how we're going to use this stuff, because I find it's a lot easier to absorb definitions when you have an idea of where you're going with it. So the idea is that we want to solve systems of equations. So someone's going to give us a system of equations, like I'm just going to make one up, like 9x minus 2y equals 11, say 7x plus 4y equals 19 or whatever. So we got something like that. And what we're going to be doing is we'll write this system of equations in the matrix equation form, ax equal b. And then the idea is that if matrix A has an inverse, then we can multiply both sides of this equation by that inverse. So that's where this idea of matrix inverse comes into play. And we know that when we multiply a matrix inverse with the original matrix, we get the identity matrix. So that would be giving us Ix equals A inverse times B. And we know also from our discussion about identity matrices that when we take I times any matrix, we just get that original matrix. So this would lead us to X equal A inverse times B. Okay, so at this point, we've used the idea of the inverse matrix, we've used the idea of the identity matrix, and we've also used the idea of multiplying matrices. So you can see how all these different ideas that we talked about just came into play in this little discussion. So then at this point, we could say, okay, like who cares about this equation? Why do we care about X equals A inverse times B? Well, what is X? It's a little column that contains your variables. And this A inverse times B would be a little column matrix that contains some numbers. So essentially, by the time you get to this point, X equal A inverse times B, what's happened is that your solution to the system has just popped out at you. So you've just got X, the value of X, and you've got the value of Y, just by doing this small amount of work here. So if we're willing to take a system, write it up as a matrix equation, we can basically just jump into this equation, which pops out the solution to the system. So over the next 2 videos, that's what we're going to be working towards, and then we'll have a fast way to solve systems. Thanks for watching.